Hello everyone. The topic of my presentation is a multi-agent reinforcement learning perspective on distributed traffic engineering. In the paper, we propose a data-driven framework for multi-region T problems. Traffic engineering is an old but popular topic. Routings are optimized based on traffic demands and the current network status so as to improve network performance or resource utilization. The two figures show a simple example of TE. By routing the traffic properly, congestion can be avoided. Of course, the example is very simple. In real network systems, T problems are much complex. The topology is irregular, traffic and the network environment change with time. So we need an automatic and smart T system. In this paper, we consider the scenario of multi-region networks. In practice, large networks are often logically or physically divided into multiple regions. Multi-region networks can facilitate decentralized management. Such a network division may be used to satisfy domain requirements or in accordance with the geographical locations and the heterogeneous routing technologies. In the figure, the routing problem is divided into several smaller sub-problems, which can be solved distributedly. In such multi-region networks, a centralized server may not be available or suitable for faster routing decisions. Each region typically makes its own local T decisions based on local network observations. As a result, the use of multiple regions makes it difficult to achieve global T objectives due to the lack of joint effort and coordination. Distributed T in multi-region networks is a very challenging problem. Existing approaches often rely on simple routing heuristics. Hot potato routing delivers traffic to the closest egress node, which may result in unexpected congestion. Distributed optimization methods decouple the global T problem and leverage iterative algorithms for distributed T, but it incurs slow convergence as well as communication overhead. As a result, these algorithms may suffer hefty performance loss under highly dynamic traffic demands. Another kind of work develops a hierarchical SDN architecture. Besides the communication cost, it still requires a controller having full control over the entire network. In this paper, we use deep reinforcement learning for distributed T in multi-region networks. DeepL is a kind of promising machine learning techniques and has the potential of dealing with complex control problems. It can exploit hidden patterns in training data automatically. After training, DeepL agents can output decisions quickly for given input. Faster inference makes it possible to adapt to traffic dynamics. DeepL agents are trained by interacting with the network environment. Typically, the agent observes network state and outputs a routing action. After the execution of action, the environment transforms from the current state to a new state and returns a reward to the agent. The goal of the agent is to learn a policy for maximizing the cumulative reward values. There have been some R-based approaches proposed for TE, but they only focus on single region T problems, and they have a single agent for the whole network. So these single agent approaches cannot be applied to the distributed T problems in multi-region networks. In the paper, we propose a distributed DeepL framework for dealing with multi-region T problems. We design to model each network region as an individual learning agent. Each individual agent has only local network information and interacts with other agents. These agents make decisions on the fly for global performance optimization. In this paper, we focus on optimizing routings within each region, and the region-level routings can be computed using existing algorithms. These agents will be trained to cooperate with each other for global T objective. To achieve the idea, we need to overcome several challenges. It's expected that good cooperative performance can be achieved, while traffic dynamics and topology changes can also be accommodated. Besides, the overhead of training and inference shouldn't be very large. In this paper, we propose a multi-agent DeepL-based framework. A feature of our framework is that we maintain 2 DeepL agents for each region instead of 1. The 2 agents decide how to deliver traffic from the ingress node to the egress node properly. The 2-agent design is based on an observation that is, network traffic in each region can be classified into 2 categories: terminal traffic and outgoing traffic. Terminal traffic remains in the region, but outgoing traffic traverses multiple regions. The routing of the 2 kinds of traffic have different impacts on the network status. Clearly, the routing of terminal traffic directly affects the status of the current region, while the routing of outgoing traffic affects the status of not only the current region, but also the other regions, especially neighboring regions, because outgoing traffic leaving the region from different border routers has different effects on the other regions. To make the agents the good policy for good T performance, we need to evaluate the quality of routings accurately. Thus, we decided to introduce 2 types of DeepL agents for each region and provide them with different reward structures. Particularly, we use a T agent to observe local network status within the region and to route terminal traffic for optimizing a local T objective. For outgoing traffic, we use an O agent to get reward feedback from neighboring regions for optimizing a cooperative T objective. Such a design is also consistent with the design philosophy of existing routing algorithms on border and interior routers. It also strikes a good balance in terms of allowing quick convergence for O agents and facilitating communication between T agents. Next, I will introduce agent development, offline training, and evaluation results respectively. First, T agent development. To apply DeepL, we need to design the state, the action, and the reward function of each agent. In our framework, we take link utilizations in the local region as the state input of the corresponding T agent. Link utilization values provide an indication of which links are congested, so the learning agents can update the current policy accordingly in order to reduce traffic and congestion in those links. Besides, link utilization being 0 indicates link failures. This makes the agents be able to deal with topology chains. Finally, link statistics can be easily measured and won't induce much measurement overhead during online inference stage. Next, we need to design action output, also routing decisions of T agent. We use routing decisions which distribute traffic demands onto multiple forwarding paths. To simplify the action space and reduce the overhead of path maintenance, we compute and construct several forwarding passes in advance. These passes connect each pair of ingress and egress nodes. Thus, the action output in our design is a set of traffic stability ratios over these pre-computed forwarding passes. However, we find that the action space is potentially very large because we usually need to make decisions for every pair of nodes in the region. When there are many nodes in the region, the action space will be very large and slow down the convergence speed. To address the issue, we distinguish elephant flows and mass flows between node pairs. For node pairs with a large amount of traffic, the agent will output routings for them adaptively. But for node pairs with a small amount of traffic, we just use static routing for them. Such a design holds the same idea of large flow-based routing in many previous works. Through this mechanism, the action space can be reduced greatly. Reward values are computed through a reward function based on current network status. A large reward value indicates that the action taken by the agent is good for the T objective. So the reward values get the update of agent parameters. Recall that our T objective is to minimize the maximum link cost of the whole network. But we didn't use the global objective value for computing reward values, because global objective values may fail to evaluate the quality of actions accurately, especially when there are many regions in the network. For example, if a T agent in some region takes an action and causes extremely high link cost, other T agents will receive a small reward value, even if the actions they took are actually good. Inaccurate rewards will mislead the learning process of T agents. In our design, the reward function is minus the maximum link cost in the local region. By keeping the maximum link cost in each region small, T agents also benefit the optimization of the global objective by adapting to the routines taken by all agents. Next, we develop all agent. The state input and action output of all agents are similar to T agents. The main difference of all agents is that we don't distinguish elephant flows and mass flows in our design. For all agents, outgoing traffic flows can affect the congestion of all regions on its path. Correctly routing a long path mass flow may even be more crucial than routing a short path elephant flow. So we make adaptive routing decisions for all outgoing traffic in each region. Recall that the routing of outgoing demands affects the traffic distribution of both local and other regions. To reduce congestion of the whole network, the reward value of all agents should not only reflect the network status of the local region, but also reflect the network status of the other regions. Therefore, we use a different reward function for all agents. More precisely, adjacent regions can exchange local rewards of T agents. The reward of the O agent is a linear combination of these shared local rewards. Note that reward exchanging only happens during training stage. After training, the agents will do inference based on local state information independently. In our design, the agents are trained by interacting with a numerical network environment. An existing DeepL algorithm called DDPJ is taken as the model of each agent. The task of each agent is to learn a deep neural network mapping from state input to action output for achieving good T performance. To make the agents be able to adapt to traffic dynamics, we reply traffic in the simulated network and change traffic traces after a fixed number of learning updates. Our framework is suitable to both centralized training and decentralized training. On the one hand, these agents can be trained in a centralized server for faster learning. On the other hand, each region can choose to maintain its own agents, and these agents can be normally trained by sharing some necessary information, including reward information and aggregated traffic information. But some sensitive internal information, such as the region's topology and link capacities, doesn't need to be shared. We do simulations by using both real and synthetic network topologies. Particularly, we use three topologies, that is Terrestrial, Full Cloud, and Bright. Bright is a tool that can be used to generate topologies randomly. For simplicity, we name the generated topology as Bright. The generated Bright topology has over 200 nodes, and thus is much larger than the other two topologies. In our simulations, traffic is generated based on the gravity model. The agents are trained and tested by different traffic metrics. By default, we consider top 20% terminal traffic as elephant flows, whose routings are taken by T agents. The weight parameter bet in the reward function of all agents is set to 0.7. For convenience, we name our proposed approach as MRTE. It means multi-region traffic engineering. We compare performance with 3 other approaches. First, we implement TRPO, which is a single agent DPL-based approach. The agent takes a window of traffic metrics as input and outputs routings for the entire network traffic. Second, we compare with hot potato routing. Outgoing traffic is delivered to the closest egress node, and the terminal traffic is routed by an existing intra-region T approach. Finally, we compare with ECMP. Traffic demands are split over pre-computed boarding passes evenly. ECMP is used to validate that multipass alone doesn't result in good performance. To compare T performance, we define normalized congestion. Normalized congestion is computed by the actual objective value divided by the optimal objective value. The optimal values can be obtained by solving a global optimization problem. This slide compares effectiveness. The left figure shows the results of the Terrestrial topology, and the right figure is about the breadth topology. Each figure shows the empirical CDF of normalized congestion. For normalized congestion, the smaller the better. Normalized congestion being 1 means the optimal value. We can see that MRT performs the best and results in congestion within 1.2 for over 90% tests. TRPO, the single agent approach, performs well in the small topology, but its performance is not stable. In the large topology, TRPO fails to convert well due to its poor scalability. We also evaluate our approach in single link failure scenarios. The broken link is selected randomly in each test. To deal with link failure, we take 2 steps in our approach. First, we set a larger utilization value for the broken link when doing inference. A large value indicates that the link is very congested, and the agents will output new actions to adapt to the link failure. Second, since some forwarding passes will be broken due to link failures, we reroute traffic on the broken path to the other passes by taking the original splitting ratios as the rescaling width. The figure shows the results of 4 approaches in all the 3 topologies. MRT gets the smallest average normalized congestion and achieves stable T performance. A feature of our framework is that we develop 2 agents for each region instead of 1. We do simulations to validate the effectiveness of the 2-agent design. We compare performance with 2 one-agent designs, that is, using 1 agent for each region. The simulations in the Terrestrial topology show that our 2-agent design reduces both global and local congestion metrics by at most 16%. We refer the readers to our paper for more details. Finally, a simple conclusion. In this paper, we propose a DeepL-based framework for multi-region T problems. 2 agents are developed for controlling the routing of terminal traffic and outgoing traffic respectively. In the future, we will investigate algorithms that can cope with more complex network environment and optimize more various objective functions. That's all. Thank you.
We didn't do evaluation in physical networks. The system is evaluated in simulated network environment. But we evaluate the cost of training time and some other costs are not evaluated.
Okay.
Yes.
I would like to see the hardware, let's say, in which platform you will be implementing it and estimate the cost of that. Okay, thanks.
Okay, thank you.
Okay, is there any other questions? You can either tap the question in the session Q&A part.
Yeah, I can answer the question in the session Q&A part one by one.
Okay. Okay, there are no more questions. So thanks for the speaker.
Okay, thank you, Center and session assistant. Thank you.
Okay, so let's welcome the second author, second paper. Is the speaker here?
Sorry, can you guys hear me?
Yeah, we can hear you. Yeah, we can hear you.
So can you see my video and I can present online?
Okay, cool.
Okay. So can you guys see the video and see the screen share?
Yeah, sure. It's okay. Now you can start.
Okay. So, okay, thanks. Okay, let me click. Okay, so hello everyone. This is Zeqi from Tsinghua University. And today I'm gonna to introduce our recent work on StarPerf, characterizing the network performance for emerging mega-constellations. Constructing new space satellite networks is gaining popularity in recent years, as satellite networks offer the promising potential to provide low latency, high throughput global internet connectivity. We observed a new wave of proposals for large constellations of low Earth orbit satellites emerge in recent years, and we have witnessed an increasing number of satellites launched targeting at provide internet service from space, and this figure shows the number of satellites launched in recent years. We also witnessed a gold round to build constellations consisting of a large number of low Earth orbit satellites, namely mega-constellations, with big players like SpaceX, OneWeb, Telesat, and Amazon entering this market. So SpaceX is currently the largest commercial satellite constellation operators in the world since January 2020. So fundamentally, the mega-constellations facilitate the internet by extending the connectivity of existing terrestrial networks and breaking the inherent physical constraints in today's internet deployment. First, satellite networks are expanding the internet coverage at broadband speed to remote and rural areas. The total system forwarding throughput is very high, and this table summarizes the maximal total system forwarding capacity of some mega-constellations in plan. Second, constellations with thousands of satellites working in LEO enable new opportunities for constructing a network in space to provide low latency communication. The free space optical links interconnect internet satellites, achieving faster data transfer in space. Free space lasers can communicate at the speed of light in a vacuum, which is 47% higher than that in glass. Roads in space can also achieve nearly shortest paths after incurring the overhead for up and down links, avoiding meandering fiber routes. So this figure shows an example. If we want to forward a packet from, for example, Beijing to Sydney, how would current internet forward the packet? If you use the trace route tool to track the packets, you can find that the packet is first sent to Los Angeles and then comes to the Sydney. So if we can use the network built up in space, for example, the Starlink, we can achieve a nearly the shorter path and achieve lower latency. So while above exciting prospects depict a booming picture of the future integrated satellite terrestrial networks, the community still has very limited understanding of the topological architecture and attainable network performance of such modern mega-constellations. But we argue that quantitatively profiling mega-constellations is meaningful for design, using, and optimizing satellite networks, but it also faces a series of practical challenges. For example, the current emerging satellite constellations such as Starlink and OneWeb are still under heavy deployments. The deployments are costly and time-consuming. Thus, it is very difficult to directly measure the network performance from a completely deployed constellation system. Also, the satellite networks have very different network features. For example, the dynamic topology and the dynamic connectivity, and the connectivity is limited by the range of inter-satellite links. Also, the constellation designs, algorithms, and network protocols are also evolving over the past years. So the fundamental problem is the community requires a modeling and profiling methodology to estimate and characterize the network performance of emerging mega-constellations under a variety of constellation designs or network policies. Such a methodology can guide the constellation operators to attain a function of the network capacity and guide content providers to deploy their service upon those emerging mega-constellations. Therefore, the main line of our work can be summarized as follows: 3 steps. First, we present StarPerf, a simulation platform for profiling and understanding the network performance of mega-constellations under diversity of architectural options and network policies. Second, leveraging StarPerf, we benchmark 3 state-of-the-art mega-constellations and their possible topological extensions, and highlight insights on optimizing constellation designs to improve attainable network performance. Finally, to further demonstrate the StarPerf's ability on understanding and using satellite networks, we quantify the potential benefits of a satellite cloud integrated infrastructure and propose low latency relay selection algorithm that can effectively reduce the latency of interactive video applications. Let's start our first section. First, we introduce the simulation platform StarPerf. The design goal of StarPerf is to explore the impact of various constellation design options, for example, the number of orbits, number of satellites, and the network policies on the attainable network performance. So this figure shows the overview of our StarPerf system. The platform takes the constellation topology, network policy, and traffic pattern as inputs, and then the output is a combination of performance metrics such as latency, throughput, resilience, and others. The main components inside StarPerf is a suite of models which quantitatively describe a LEO satellite constellation together with its performance estimation. Moreover, StarPerf allows users to perform what-if analysis and explore the design trace space of emerging mega-constellations. Here is how we characterize the network topology. StarPerf leverages 5 primary parameters to describe the constellation OPTA elements, including the inclination, attitude, orbit phase shift, number of orbits, and the number of satellites in each orbit, just like listed in this table. In addition, each satellite may have several inter-satellite links for interconnection. So we use the number of ISLs and their interactions to describe the satellite connectivity. The network performance over satellite networks is affected not only by the design of constellations, but also by the network policies running on satellite networks. So users can set the routing policy to determine how data packets are forwarded from the source to the destination over the LEO satellites. StarPerf builds a grid system upon the Earth's surface for modeling and analyzing geographical information to estimate the area-to-area network performance metrics. It uses the fraction of covered hotspot area to quantify the hot coverage range. We focus on the attainable latency while routing over satellite networks and estimates the area-to-area latency from different areas. It also estimates the area-to-area throughput to quantify the ability of a certain constellation topology to deliver contents from area I to J. for example. We also use the Bertrini's centrality to indicate the ability to provide and maintain an acceptable level of service in the face of force and challenge to normal operations. User requests are formulated as a traffic metric in the grid system, and the StarPerf automatically scale to enumerate all the possible design options. For example, increase the number of satellites or enable, disable the inter-satellite networks. For more details of our performance model, we encourage you to read our paper to get more details. We have implemented the StarPerf mainly in Python. This figure plots the key components in StarPerf implementation. The network simulator is partially implemented based on a third-party orbit analysis tools, for example, STK tool, which help to simulate the movement of satellites over time. Once all nodes of the network have been loaded and scaled to the desired size, user traffic is then generated and applied to the network, and finally, StarPerf calculates the corresponding network performance. Okay, so now we have our simulation platform. That's good. So next, we introduce the second part of our work. Leveraging StarPerf, we benchmark 3 state-of-the-art mega-constellations and their possible topological extensions, and highlighting insights on optimizing constellation designs to improve the attainable network performance. So this table shows the primary constellation parameters of the mega-constellation selected in our benchmark, for example, Starlink phase 1 and the OneWeb and the Telesat, including the polar and inclined orbits. This is the primary parameter, including the inclination, altitudes, blah, blah, number of orbits, and others. So this figure depicts the hot coverage rate of different constellations aggregated by latitude and longitude, respectively. The global population distribution is extracted from the graded population of the world, version 4. All 3 constellations can cover large population centers. For example, the population which is larger than 57 million. So the right figure shows the number of satellites in line of sight per million population, aggregated by latitude or longitude, respectively. This metric indicates the geo-distributed coverage rate in different areas. And the Starlink has the largest number of the satellites per million population, around the -45 latitude band, just like this. So here are the results of the latency obtained between some populated areas around the world. We choose some big cities, for example, New York City, Sydney, London, and Beijing. So we can learn from the result that the emerging mega-constellations can provide routes with low latency for long-distance intercontinental communication as compared to terrestrial internet. Routes over the satellite networks may suffer from high latency variation. This is because the satellites move in high speeds in the space, and the physical distance between 2 nodes is enlarged and shortened over time, resulting in the latency change. Moreover, the variation is highly affected by the topology design of the constellation. An even constellation pattern like Starlink can obtain lower latency jitter as compared to the Telesat. And this is the result of the throughput. Yeah, also it's it's an area to area throughput. For the given area pair, Starlink, OneWeb, and Telesat can provide 11, 10, and 6 Gbps average throughput respectively. As the uniform architecture design of Starlink enables better flexibility to accommodate traffic on alternative low latency paths. On average, Starlink can achieve highest area-to-area throughput as compared to the other constellations if ISLs are enabled. So this is the result of resilience. Since satellites in Starlink are distributed evenly, all nodes have similar Bertrini's in Starlink, indicating a good resilience that Starlink can provide and maintain data forwarding in the face of node or link failure. Now we conclude some 2 insights obtained from the benchmark. Emerging mega-constellations indeed offer low latency opportunities for long-distance communication if ISLs are deployed, especially for communications between different continents. The attainable network performance can be significantly affected by the concrete constellation design. Satellites working on lower orbits may provide lower latency due to the shortened route length. However, low orbits are also faster with a higher orbital velocity, which is more likely to cause intermittent network connectivity and higher jitter. Thus, the constellation design and network policies should be jointly optimized to support various upper layer applications. Second, the orbital decision and the scale of satellites can also significantly affect the resilience of the constellation. An even constellation design, for like Starlink, has more nodes with lower bitrate in the constructed network, indicating that failures occur on those nodes may have smaller impact on satellite networks traffic. To guarantee good network resilience and keep stable connections, it is recommended to keep a balanced constellation architecture with an evenly coverage. So finally, to further demonstrate StarPerf's ability on understanding and using satellite networks, we quantify the potential benefits of a satellite cloud integrated infrastructure and propose a low latency relay selection algorithm that can effectively reduce the latency of interactive video applications. Here we use a use case to show how StarPerf can be used by the content providers. So over the past several years, we have witnessed a number of internet-based real-time communication applications, let's say RTC applications. So a classical solution to reduce the communication latency, especially for long-distance cross-AS communication, is the relay selection, which the underlying idea is that use an intermediate server to relay the RTC traffic, like this figure shows. So we do not allow two attendees to communicate directly and just use some relay. Just for example, some applications just like the Zoom work in this way. So the relay selection problem is to follow two stages. First, to find a relay server which is good enough for all attendees, and then each attendee communicates to each other via the relay server. So here we want to ask the question. Our previous results have shown that the LEO satellites have the potential to provide low latency. So can we put the relay on LEO satellites? So our relay selection approach in the satellite cloud integrated architecture can be summarized as follows. The key intuition behind our approach is the insight that we have identified in previous results that leveraging satellites running on the low Earth orbit can potentially build a low latency path for long distance communication. So here are the three key steps. So periodically, each attendee explicitly probes the latency to every relay options. The performance information for satellite relays are provided by the StarPerf. Then, when initializing an RTC session for a set of attendees, the session controller explores historical performance information to calculate the optimal relay selections. And once established the RTC session for all attendees based on the relay server selected, performance feedback of the RTC session is then sent to the session control server. Here are some numeric results. So to conduct this evaluation, we first extend the WebRTC to support communication via a relay server. We use TC, which means traffic control in Linux, to tune the link quality between the relay server and the laptop and simulate the link performance. For example, we simulate the RTT and bandwidth over time. We simulate the communication between three populated areas, New York, Sydney, and Beijing. Cloud-based relays are based on Amazon AWS, and the satellite-based relays are simulated based on the Starlink Phase 1 constellation. So this figure shows the results, and this is the frame latency. The lower, the better. This is the funding, and the interactive frame latency is calculated from the time when a video frame is encoded and sent to the transport layer on the sender to the time when the same frame is assembled on the receiver by exploring the relay options hidden in the satellite cloud infrastructure. Our approach can effectively reduce the end-to-end interactive latency by up to 62% from the long-distance communication. Okay, so finally, let's conclude our work. In this work, we first present StarPerf, a simulation platform that enables constellation manufacturers and content providers to estimate the achievable network performance under a variety of constellation options. Then we propose a novel approach that can profile the time-varying network performance under different constellation options. Leveraging StarPerf, we evaluate and compare the performance of 3 state-of-the-art LEO constellations to obtain insights on network optimization for mega-constellations. Based on these insights obtained, we further propose an adaptive relay selection algorithm that intelligently chooses on-satellite traffic relay to reduce the end-to-end communication latency. The data-driven simulation shows that by properly selecting an LEO satellite as the network relay, end-to-end communication latency can be reduced by up to 62%. Okay, so our StarPerf is open source, and this is the GitHub link for the repository. And thank you very much. You are more than welcome to ask any questions about our work. Thank you.
Okay, is there any questions? Okay, let me ask a question first. So, can you hear me?
Yes. Go on.
Because this is a simulation platform, so I'm wondering, how rare is this simulation? I mean, how do you know you really replicated the real network, every details? I mean, maybe it's very probably you miss some very important factors, and that maybe the entire platform maybe give the wrong evaluation results. I mean, how do you evaluate this?
Thank you very much for the good question. It's a quite good question. So to be honest, currently, yes, our solution is the simulation platform, and like other recent works on the emerging networks, for example, those papers published on hotnets and connets, our performance results are obtained from the model-based estimation, in which satellites and orbital configurations are based on the public real data released by the satellite operators or other astronomy community. The difficulty is that today's mega constellation, for example, the Starlink and OneWeb, are still under very heavy development. And currently, the Starlink cannot provide any public available access, so we cannot get the real data from there. So just use the estimation and the model base. We also compared our results with the previous work and maybe some other simulation tools from the astronomy community to keep consistent over the data results. So as our future work, we will check the evolution of Starlink and other similar mega constellations and upgrade our solution to follow the latest upgrades and improve the fidelity by calibrating the performance results if one day Starlink offers available public access in the future. Okay, thank you.
Any other questions? I think there is a question in the session and Q&A part. Did you see that?
Oh, sorry, I'm using the Zoom client, and you mean the website?
Any method to model the satellite is by Zhongqi. The question.
Oh, you are so you're asking the details of the
satellite.
Okay, so first we can get the satellite orbit data. For example, the inclination and orbit altitude and how many orbits, how many satellites in orbit. So if we get these basic parameters, you can calculate their circle and you can simulate the movements around the Earth. And there are also some third-party computation tools, for example, GMAT and the SDK, that these tools from the astronomy community, they can help to calculate the movement of those satellites.
Okay. I remember, let me ask a question. I remember the TC meeting asked you to open source the simulation platform, right? Did you share the not to share the link at the PPT or?
Yeah. This page. Can you see this?
Okay. Okay. So it's publicly available.
Yeah, it is available, and we will keep upgrading the data because the manning. So manning the state-of-the-art constellations are still under heavy development, and the SpaceX will have many launch plan in recent months. They have already about 600 satellites in space currently.
Okay, so thank you. I think there is no more questions. Okay, thank you for the
thank you very much.
speaker. So okay. So the next paper is from Hong Kong University of Science and Technology. So is the speaker here?
Yeah, I'm here.
Okay, finally we got a girl here. Thanks for coming. And you're gonna do it live, or you can do it live, right?
Yeah, I can present online.
Okay, cool. Okay, you can start now.
Okay.
There's a share screen button. Yeah.
Okay, I can see the screen.
Okay. Can you see the screen?
Yeah, I can see it.
Oh, okay. Hello, everyone. Welcome to my talk. My name is Yuqing Li from Hong Kong University of Science and Technology. It's a great honor to present our work, Online Cooperative Resource Allocation at the Edge, a privacy-preserving approach. So, our motivation for doing this work is that edge computing has emerged as a new computing paradigm to support resource-intensive yet delay-sensitive applications at the edge, especially those that cannot be served efficiently by conventional cloud computing due to unpredictable latency or extensive bandwidth. Edge computing provides a platform that facilitates resource-constrained edge servers to pool their resources locally for cooperative computation. A common practice for improving capacity is to establish computational facilities in proximity to users, but it may cause resource waste or high construction cost. This motivates us to design open infrastructure, where individual servers like PC or even smartphones can conveniently contribute to capacity while economizing their valuable resources. One of the examples is VectorDash, a commercial platform allowing GPU owners to rent out GPU instances. Note that each agent can either share idle resources or utilize resources crowdsourced, or do the both if its capability allows. Therefore, one fundamental problem is how to optimally allocate edge resources to satisfy user demands in competitive environments. This forms a double-sided market-based allocation problem, which is also the main focus of our work. The framework of such open edge market consists of a platform and a set of servers to share idle resources for profit, and a set of users to pay for using edge resources for computation offloading. Here, the platform is authorized to manage server payment and allocate the crowdsourced edge resources to users. Existing works focus on isolated round markets, making them simple and easy to implement. But in practice, the decision must be made in real time for two reasons. First, continuously generated requests need to be processed promptly. Second, user mobility, random arrival and departure, time-varying resource supplies and demands may lead to the market dynamics. Let's look at a toy example. Users submit bids to compete for edge resources, and as the auction comes out that users I1, I2, I3, and I4 are allocated to servers G1, G2, G3, and G3 respectively. Assume after a while, a user I1 moves to the coverage of server G3. If its task is still offloaded to the server G1, then there may be allocation inefficiency or market failure. In this case, edge resources should be dynamically reallocated to follow the market dynamics. And this brings us to another issue, cross-server migration. However, multi-round bidding will incur possible privacy leakage. Despite a trusted platform, there could exist honest but curious agents who follow their mechanism strictly but attempt to gain additional information. By regulating its own bid in multiple rounds and comparing the outcomes, a curious agent could infer other bids' knowledge, which contains a lot of personal and private information, such as users' interested services or willingness to pay, and servers' network configurations or business strategies. Therefore, the bid privacy issue, if not properly addressed, will discourage privacy-sensitive agents from participating in the market. For these reasons, we try to develop an online privacy-preserving double auction mechanism to facilitate dynamic resource allocation at the edge. Different from existing online market schemes designed for truthful resource trading, we consider a more complicated market under energy, proximity, and capacity constraints. Besides truthfulness, we also address the issues of privacy leakage and system uncertainty. On the other hand, existing works on bid privacy mostly assume single-sided markets or only achieve single or round differential privacy, while we consider a double-sided market to offer privacy guarantee for both agents and also provide real-time privacy protection across multiple rounds. Let's look at this picture. Suppose there are M users competing for key types of resources from N edge servers. The time is discretized into slots. In every slot, one round of resource trading is carried out. Each user submits bids to the platform specified by its desired resource bundle and valuation. Meanwhile, edge servers participate in the market by submitting asks specified by the supplied capacity and resource cost. For any slot T, the market model can be captured by bipartite graph GT. To realize several computation offloading, the connections between users and servers are subject to latency, energy, or geographic region constraints. Given all submitted bids and asks, the platform needs to make allocation decisions. The binary variable xigt equals 1 if user I is allocated to server J in slot T. But as there is one problem with that. Dynamic allocation may lead to the redistribution of user requests. Let's still look at this example. When user I1 moves out to the server's G1's coverage area, The service is migrated to a different server. This will consume energy and incur migration cost for connection reestablishment, which can be troublesome for mobile devices running on battery. To capture such energy consumption, long-term performance optimization is needed. That is, to derive the optimal allocation in multiple rounds instead of a single round by incorporating the energy efficiency into the formulation. So we formulate online allocation problem as a social welfare maximization problem subject to capacity and long-term budget constraints. Here, omega IJT is the net benefit of offloading user I to server G. And BI is user I's energy budget, which is the upper bound imposed on its overall migration cost. Actually, it does have two other inherent constraints: truthfulness and privacy. The former is due to agents' strategic behaviors, and the latter is to offer bit privacy guarantee. And this problem is NP hard, even if all omega IJTs are known. Given system uncertainty, the decisions have to be made without forcing future bidding information, thus leading to suboptimal allocation. And the long-term energy budget imposed on users further complicates their decisions across slots. To solve these challenges, the mechanism OPTA is proposed. So the workflow of OPTA goes as follows. For any slot T, agents first submit bids or ask to the platform, which may be different from the real ones. The platform then determines the winner set WT and prices, including chart profile QT for users and payment profile PT for servers. The bid-ask pair IG wins, meaning that user I is allocated to server G. After announcing the auction outcome to the agents, the platform then requests resources from each winning server to serve its allocated users, and then pays or charges them. Here, multi-round truthful bidding may cause privacy leakage. So the design objective is twofold. The first is differential privacy. For any two inputs differing in only one bid or one ask, OPTA gives epsilon delta differential privacy if for any possible outcome, this probability constraint is satisfied. The smaller epsilon delta, the closer to probabilities, making it harder for the adversary to distinguish between two inputs. There are two ways for differential privacy. The first is to add noise to output, but which might not be feasible after adding noise. The second is to introduce randomization to output via exponential mechanism. The output is randomly selected through a score function FAB, mapping a pair of input A and possible outcome B to a real value score. The mechanism gives to epsilon delta differential privacy if it randomly generates the outcome based on such exponential probability. In addition, OPTA is supposed to satisfy essential economic properties, including truthfulness, individual rationality, and budget balance. The agent utility is defined as UIT and UJT. Considering exact truthfulness is too restrictive to be compatible with differential privacy, we thus adopt a weaker but more practical gamma truthfulness, such that no bidder can gain more than gamma utility by bidding untruthfully. As for individual rationality, it is also expressed in terms of expected utility. And to make the market self-sustained, OPTA is expected to be budget balanced. Given system uncertainty in future market behaviors, Competitive analysis is designed to decompose the online education problem into a series of single-round auctions. Here, SPTA is repeatedly invoked to derive the optimal outcome of all slots jointly. And the long-term energy budget constraint affects allocation decisions over time. If a user's budget runs out, some feasible pairs may become invalid. In this case, it can only be served by current server and cannot be switched to other cost-effective ones. This negatively impacts the social welfare. An individual situation is that user budget is sufficient for all slots so that the best decisions can be chosen from all feasible pairs. To this end, we introduce a scaled benefit for each pair, and iteratively adjusts them based on user residual energy budget. Here's a regulation factor, KIGT, is updated if there exists migration, and remains unchanged otherwise. In this way, the bid from a user with a smaller residual budget will be assigned a smaller scaled benefit, thus reducing its chance to win. Okay, let's look at how to design SPTA. We first reformulate the NP-hard single-round social welfare maximization problem without long-term budget constraints. Here, the net benefit omega IJT is modified to a scaled benefit given by OPTA, such that the objectives of different slots are iteratively adjusted to capture the temporally coupled nature of the problem. So SPTA is expected to give efficiency, privacy, and truthfulness guarantees, whereas Form 2 are realized by heuristic-based differentially private allocation, and the latter one is achieved via critical value pricing. Exponential mechanism is designed for differential privacy by randomizing the output. Compared to pricing randomization based on uniform pricing, randomizing the allocation would be more applicable in double-sided combinatorial edge markets. Intuitively, a more socially efficient pair that generates greater social welfare with less resources is more preferred. We thus construct a score function, RAJT, to evaluate each bid other pair as a contribution to the social welfare. The algorithm is shown as follows. Firstly, initialize a winner set and construct a list containing all feasible pairs. Then iteratively select winners until no pairs can be selected. In each iteration, eliminate redundant pairs and assign each remaining pair a selection probability defined based on a score function. In this way, a pair contributing more to social welfare will be assigned a higher probability. After that, randomly select one pair by the probability and update the corresponding parameters. Critical value pricing is first applied to guarantee truthfulness. It charges the winners the highest price of losing competitors. Specifically, we first initialize the price sets and sort of feasible pairs in descending order of score. For each winning user, construct a new sorted list containing all feasible pairs except for redundant ones with it. Then calculate the prices of losing competitors for its desired bundle and select the smallest one. And the payment for each winning server is computed by accumulating charges of associated users. So we will skip the analysis of the proposed mechanism and directly talk about some results. Firstly, we prove that OPTA provides epsilon t delta t differential privacy for user evaluation and server cost. and it is also gamma truthful for both agents. Moreover, OPTA is an individually rational and budget-balanced online double auction mechanism that gives a provable competitive solution to social welfare problem in polynomial time. So let's come to simulation. We first compare single-round SPTA with 3 benchmarks. The first is OPT, which uses MIP solver to obtain the optimal solution. And the second is greedy SW to pursue the maximum social welfare while greedy heuristic. And the last is greedy A, which greedily allocates as many users as possible. From this figure, we observe that SPT and greedy SW achieves near optimal social welfare. And SPTA is inferior since winners are chosen by selection probabilities to enforce differential privacy. And the results shows that SPT achieve higher user satisfaction close to the highest one yielded by greedy A. And a good trade-off between performance and efficiency is also provided. For online auction, the competitiveness is captured by the ratio between offline optimal social welfare and its achieved overall social welfare. The results shows that OPTA provides near optimal social welfare and performance stability. To evaluate privacy performance, we define the privacy leakage as the KL divergency of 2 outcome probability distributions. The smaller privacy leakage, the harder to distinguish 2 inputs, indicating a better privacy performance. From this figure, we find that there exists a trade-off between social welfare and privacy leakage. And the left figures show that users and servers achieve non-active utility, suggesting individual rationality holds for both agents. To validate truthfulness, we randomly pick an agent and allowed it to submit a bid or ask whose valuation or cost differs from the true one, and implement OPT on such untruthful dataset. The result shows that the agent has no incentive to bid untruthfully. That is, OPTA is truthful. In conclusion, we are the first to study the market-based dynamic resource cooperation at the edge with a near optimal efficiency and bid privacy guarantee. The proposed competitive online algorithm uses single-round auction as a building block towards an adaptive market which dynamically allocates resources upon system change. And the desired properties are validated through rigorous theoretical analysis and intensive simulations. So this is my presentation. Thanks all.
Okay. Thanks for the speaker. Is there any questions? Okay, maybe I will ask the first question. So what's the difference? I mean, in the cloud data centers, there are resource auctions similar. So what's the major difference between edge computing and cloud resource auction? I mean, why is all this auction happens for each edge server or edge site separately, or can we do auctions for multiple edge sites together?
Okay. Thanks for a question. Yeah, cloud computing maybe designed most cloud computing schemes designed for the truthful resource trading. But in this paper, in edge computing, it is a more complicated case. We need to consider some practical communications issues like the energy, the proximity, and some capacity constraint. The capacity of each edge server is very limited compared to the data center. Yeah. Cloud computing, we also designed the resource allocation as the maybe the centralized incentive mechanism. But in edge computing, we need to consider the more decentralized setting.
I have a question.
Okay.
I just got lost due to your complicated math and those models. Can you intuitively introduce your idea how you can preserve privacy essentially? And especially you say it's a differential privacy. And I mean, from the formulas, I don't get it, but can you intuitively tell us without any formula, can you just tell us how your auction-based approach would be able to address that?
Yeah, to enforce differential privacy, there are two methods. The first one is to add noise to the output. But in resource allocation, maybe introduce after adding the noise, the allocation may not be feasible. So in this paper, we consider the second one to introduce the randomization to the output. Because in this paper we address a more complicated combinatorial double-sided edge markets. So if we randomize the pricing, we cannot find maybe the targeted the price for to randomize. So in this paper we randomize the allocation. We in resource allocation, the allocations are servers, the user to servers. We introduce the randomization to the user the request allocation.
So the privacy you are going to preserve here is about how much you allocate for the particular client. Is that your objective? Or typically the privacy is aiming at anonymizing the identity. Now you are anonymizing the resource allocated. So I just don't get, is that your point, or I want you to clarify here?
Yeah, this paper is focused on preserve the identification and the privacy. Mm-hmm. We introduced randomization to the allocation such that for a particular outcome, we cannot identify which one maybe the user or the agent the bid from which one. Mm-hmm. Because the outcome of two different inputs are the same, we cannot identify which bid submitted by the.
Thanks. I will read the paper and see. Okay.
Okay, no more question? Is there any new questions? Okay, I think that's all. Thank you very much. Thanks for coming today.